Welcome to the office. We want to take a look at an example of a permutation on a set. And from that permutation, we want to find the equivalence classes of the induced equivalence relation. So let's take a look at our notes here. Excellent. We have a permutation sigma on the set A, which is the numbers 1 through 10. All right. If I want to find the equivalence classes, what I can do is I can just pick a number and work from there, okay? So I can say, what are the things related to 1? Okay. Our formal definition of an equivalence class is going to be the set of all things B in A, which is, again, A is simply all of these things up here. 1, 2, 3, all the way up to 10. So it's all of the things in A such that sigma to some power of 1 is um, equal to B, or some n, which is an integer. Not fixed, it can be for some, okay, for some integer. So in other words, all that I have to do is go ahead and start saying, well, what are the things related to 1? Well, anything raised to, or when I take sigma and I raise it to the 0th power, I can recognize that 1 is related to itself. But and that's good. So we can start off with 1. But then what does sigma do? Sigma, the first time we run it, sends 1 to 2. So 1 is related to 2. Fantastic. Now, when I run sigma again, sigma squared is going to take 1 to 2, and then it's going to take 2 to 5. Okay, so sigma to the second power of of sigma of 1 is equal to 2. Boom. Sigma squared of 1 is equal to sigma of 1, which is sigma of 2. Sigma of 2 is 5. And we continue on in that fashion. So I don't have to write this out every time. I just have to watch and see where these things go until it stops going somewhere. So 1 gets sent to 2, 1 gets sent to 2, 2 gets sent to 5, 2 gets sent to 5, 5 gets sent to 1, and that actually puts me back at where I began. I don't have to list those elements twice. So I'm done. Now, the equivalence class containing 2 is exactly this equivalence class. So the next number that I come up with is 3. So I'm just following along so I can make sure I hit everything. So I already got 1. Technically, well, not technically, but I do already have 2 and 5 now. So I don't have to worry about those. The next equivalence class is the equivalence class containing 3. So I can start off with 3. 3 is related to 9. Through sigma. When I take sigma squared, 3 goes to 9, and then 9 goes to 7. And then I can, of course, just continue on. 7 goes to 4, 4 goes to 3, and that puts us back at where we started. So that's our equivalence class for 3. Now I have 4 taken care of, 3 taken care of, 7 taken care of, 9 taken care of. So the next one I get is 6. 6 is, related to itself. So 6 goes to 6, and that's it. You're done. What about 7? Oh, I already got 7. So 8. Oh, well, 8 does the same thing. 8 goes to 8. So the equivalence class containing 8 is just the element 8. Because 8 goes to 8. You're done. Same thing for 10. All right, so that's it, right? Our equivalence classes, if you're not recalling at the moment, the square brackets say this is the equivalence class containing whatever is written in between the brackets. So this designates the equivalence class containing 1, the equivalence class containing 3, the equivalence class containing 6, and so on. And again, this is our definition here for an equivalence class. And then when we follow through on that definition for our current context, we find this set and so on. All right, that's it, right? That's all that we wanted for now. Pretty simple example, and that's it. We're going to share another or a new definition in the next video and run through a couple of examples that are pretty much the same thing. So that way we can familiarize ourselves with the language of this section. So I'll see you back in the office in just a moment.